welcome to my talk on how your brain is conspiring against you making good software. So again, I'm an engineering manager at DigitalOcean, and if you aren't familiar, DigitalOcean is a New York-based company that tries to take the cognitive load out of managing your infrastructure. I'm also an organizer of a JavaScript conference in New York City called Empire.js, so I know firsthand just how much work, time, effort, dedication goes into making a conference a reality. So could we get a round of applause for all the organizers and volunteers of French Friends? You can also find my slides on the internet if you want to follow along, so you don't have to worry about taking copious notes. And also, you can tweet at me at Zeigen Vector with all of your questions, comments, and concerns, and I'll get back to you as soon as possible. All right, so funny story. On Wednesday, the one-liner to introduce one of the talks was, "Humans are bad at computers, and this is how we could be better," or something like that. And I literally said out loud, "But that's my talk." And then I realized it wasn't the same talk at all. So what is this talk about? Well, before I was an engineering manager, and even before I'd written a single line of JavaScript, I was a cognitive science major in university. And what is cognitive science? It's the study of thinking, decision-making, attention, vision, consciousness, and my personal specialty, human language processing, which is why I love puns so much. But if you were to ask me to sum up what I learned in those 4 years into one concise sentence, it would be that humans are predictably irrational, which is a phrase that was coined by psychologist Dan Ariely, who wrote a book by the same title. But what does this mean? It means that we employ tricks, patterns, and shortcuts that allow us to make more predictable and allow us to make more decisions. But this fast thinking causes us to not be so rational in our judgments all the time. Causes us to make what Amos Tversky and Daniel Kahneman, two other prominent scientists in the field, call severe and systematic errors. And these errors are cognitive biases. And talking about cognitive biases has become kind of hip in this industry. So if you've heard of that term, this is what those cognitive biases are. So I'll be talking about some of these, as well as some other ways that our brains get in our way. But this isn't a psychology conference. We're here to talk about front ends and software. So look, why am I on stage talking about how our brains work? Well, because software is about people, as my friends at And Yet say. Software isn't just about code. We make software, when we are humans, we make this software for humans and with other humans. So my job as an engineering manager is to make sure my team that is made up of humans is happy, healthy, productive, getting along with each other, is growing, that the people are challenged, and that they're growing in their careers. My team is like my product. So I started thinking about, how could I use this education to my team's advantage? How can I help use all the stuff that I know to help make my best team the best team it could possibly be? So I started thinking about these cognitive biases and other quirks of our mushy human brains, and how they affect us as we're making software in the environments that we're supposed to be making software in. Because even the most calculating of software engineers is a human, and therefore subject to these cognitive biases, no matter how much they think that they are immune to the irrationalities of humankind. So over the next bit of time, I will talk about these things, starting with logic. Because, logic is one of the fundamental underpinnings of programming. You have if statements, else statements, booleans, ternary operators, but computers can only do what humans tell them to do, and it turns out that humans are not very good logical thinkers. One of the tools that psychologists use to test this is called the categorical syllogism, and one is up there on the screen. So a categorical syllogism is a logical argument beginning with two premises and ending with a conclusion. So psychologists would ask the participants, hey, does the conclusion follow from the premises? So I'll give you a chance to figure that out for yourself with this one. So in this case, 81% of people said yes, the conclusion follows from the premises, 10% said something else wrong, and only 9% of people got it right. It's not very good. We don't get very much better when reasoning about complex if-then statements either. A psychologist by the name of Weissen created this task in which he presented 4 cards, and on one side of the cards was a letter, and on the other side was a number. And he asked participants to evaluate the following rule. If a card has a vowel on one side, it has a number on the other. And then he asked the participants what cards needed to be flipped over to check that this rule checks out. So I'll give you a chance to figure that one out. So only 4% of people got the right answer, which is to flip only the A and the 7. So if you're stumped about why this is right, remember that the rule says nothing about what consonants have to be paired with. But luckily, there's some hope, which is that we get better when reasoning about concrete logical examples. So some scientists adapted Weissen's 4-card task to test the rule. If a person is drinking beer, they must be over 19 years old. I think this was done in Canada. And in this case, 73% of people got the answer right. So a little bit better, so I guess there's hope or something. So when we inevitably make a mistake in our code, because after all, we're human, we're going to have to try and debug that code. But as computer science celebrity Brian Kernighan once said, debugging is twice as hard as writing a program in the first place. And why is this? Well, I think there's some cognitive biases that are getting in our way. One of them is the confirmation bias, that we have this tendency to search for, interpret, favor, and recall information so that it conforms and confirms our pre-existing beliefs, while disproportionately giving less consideration to alternative hypotheses. In an experiment, Weissen, again, presented subjects with a series such as 2, 4, 6, and told the participants that the trio conformed to a specific rule, and their job was to figure out what the rule was by asking if other trios of numbers conformed to the rule. In reality, the rule was actually pretty simple, just that the numbers had to be in ascending order, but people had a lot of trouble with this for some reason, probably because they would just ask about trios that confirmed the rule that they already had in their mind, such as 8, 10, 12, but not ask disconfirming questions like, hey, does 2, 2, 2 work, or 2, 3, 4, or 1, 2, a million? So those who did ask questions that tried to disconfirm the rule that they already had in their head did significantly better. So what does this mean also, in addition to how this affects us for debugging, what does this mean for when we're testing our code so we don't end up with bugs in the first place? We also tend to scrutinize disconfirming evidence, trying to find flaws or ambiguities, blaming, say, a bug in the library or someone else's code that we're trying to interface our own code with. And even when the facts are clearly stacked up against the belief that we hold to be true, we often throw out those disconfirming facts. And this effect is stronger for emotionally charged issues, such as when your code is wrong. We also often have no idea we're going to solve the problem soon, even 30 seconds before we crack it. And this frustration feeds back and makes it harder and harder for us to think clearly, and therefore harder and harder for us to solve the bug. Scientists found that this was true when they gave subjects insight problems, like word problem, brain teaser type things. And then as they solved the problem, the scientists asked the participants to rate their progress in terms of warmth. So initially, participants gave ratings of 1 or 2, and then their ratings abruptly spiked when they got an answer, whether it was correct or incorrect. We also have a tendency to approach problems in a particular way, and this is called our mental set. And our mental sets are shaped by our experiences and habits. So if we wrote the code, when we go back to try and debug it, we'll be thinking through the problem in the same way as when we initially wrote the code, and it's going to be harder to think outside the box and squash the bug, especially if it's on a more conceptual level. So like, I know I'm guilty of replacing a single equals with a triple equals or forgetting to set the equals 0 when I'm setting up my loop. So that's like a fairly easy bug to figure out. Imagine if like the bug was actually a flaw in the way that you were thinking about it, and that's like the way that you were, programmed to think about it. So one way I like to advocate to getting around this is to pair on squashing bugs. It's likely that your friend or colleague is going to have a different mental set, and therefore might help you find your bug faster. Also, it's a good idea to take a break. I know when I'm trying to solve a bug, I just want to sit there and finish it, sit there until it's over and solved, and then I can be on my way doing the more fun things. but it's actually good for your brain to get up and take a break, because it helps you forget the things that are holding you back. To test this, psychologists gave participants puzzles to solve, as well as misleading hints about the solution. So one group had a minute to solve the puzzle without breaks, and another had 30 seconds of solving the puzzle, were interrupted for a short bit, and then had another 30 seconds. It was found that the interrupted group did better, and that they were less likely to remember the misleading hints. So squashing a bug is it's a form of problem solving, and problem solving is often linked to creativity. So what exactly is creativity? Well, in short, it's really nothing special. It's just when the sum of your experiences, memories, training, and motivation come together in the right way. It's about your associative memory. So I mentioned that you might be on a team working with other people, and that means you might have to read someone else's code, especially if you are helping them squash their bugs. But reading someone's code is like getting in their head, but they most likely had a different mental set, a different way of approaching the problem than you would have approached the problem. And this is going to be hard for us to really get into that state of mind, because again, we tend to think of problems in fixed ways. Another instance in which we might be using someone else's code is when we decide to use a library and then have to read the source code, or even just using the library in general. Or reverse to this, because I think in the industry we call it not invented here syndrome. Psychologists call this the IKEA effect, which was named after an experiment in which scientists asked participants to assemble IKEA furniture, build Lego contraptions, fold origami, all sorts of arts and crafts. And then they were asked how much money they would pay for their creations, as well as for expertly made creations. Participants, they found, were willing to pay similar amounts of money for their finished, amateurish, dilapidated creations as they would for experts' creations. And while this experiment was only talking about monetary value, I think it's fair to extrapolate to value in general, but how much we value things that other people have made. Again, this is getting in our way when you just value the library that was homegrown versus the one that's been battle tested and has all of the edge cases that have been used in production. So you're working with other people on a team, and maybe you have an engineering manager or a project manager, and they want to ask you how much time you think it's going to take to finish the project that you're working on. But it turns out that we're really bad at estimating how long it's going to take us to do something, and this is called the planning fallacy. So a scientist asked 37 psychology students to estimate how long it was going to take them to finish their senior theses. Remember, these are psychology students, so they probably have learned about the planning fallacy. Their average estimate was about 34 days to finish their thesis, but in reality, it took them on average 56 days, with only about 30% of people finishing in the time that they predicted it was going to take them. So this phenomenon also occurs regardless of if we know that past tasks of a similar nature have taken longer to complete than generally planned. And this also only happens with our own tasks, whether personal tasks or individual tasks, or tasks of a group that we are involved in. For other people's and groups' tasks, we show a pessimistic bias. So we think it's going to take them longer than it actually will. This is a result of a larger cognitive bias called the optimism bias, in which we think that bad things are more likely to happen to other people than to us. And this isn't just seen in the planning fallacy. It's also seen in, we think that we're less susceptible to crime, we're less susceptible to the whims of the stock market, less likely to get sick, all sorts of things. But that just simply isn't true. We're also loss averse, which means that when we think about the costs involved in a decision, we tend to focus more on what we will lose than what we will gain. This comes particularly true and is relevant to our work and planning our work in the sunk cost fallacy, which is that we are often so worried about wasting already invested resources, like time, that we don't consider the loss of continuing to invest more, even if the project isn't going very well and should probably be scrapped. So once you've left that planning meeting, you go back to your desk to do some work where the person next to you is on a Google Hangout with the person next to them. And so, you're in an open office, so you can hear them. You might be able to tell, I'm not such a fan of open offices, so I'm going to start off with an anecdote that initially doesn't seem to help my case, which is that we're actually pretty good at filtering out unwanted things. And this is called selective attention. And scientists have tested selective attention by doing what's called a dichotic listening task with shadowing. So the idea is that participants have say a stream of speech going in one ear and another stream of speech going in the other ear, and they're supposed to repeat back something coming out of a particular ear, like that. And it's found that participants have little memory of the semantic content, so of the meaning of the ear that they were supposed to be ignoring. So a switch from English to German goes unnoticed. But we do pick up certain things. So we remember, say, physical attributes of the speech. So, for example, people are generally able to remember if there were words or not, or if it was just music or sound. So if you're focused on writing code and there's music playing, you might notice that the music is playing, but you're not really comprehending the words. But if there's something salient, so something might grab your attention, like your name, then you tend to notice that. And this is called the cocktail party effect. This suggests that we're actually processing the stuff that we're ignoring. So it goes into our ear, we actually process it, and then we throw it out. So there are mental resources being dedicated to processing the things that we are trying to ignore. So this means that there are fewer mental resources being dedicated to what you're actually trying to pay attention to. Because we actually have a limited amount of mental resources, and we're putting active mental effort into blocking the stuff out that we don't want to be hearing. So, you're unlikely going to be able to keep writing that difficult algorithm when, 5 feet away, people are having a conversation about how they're going to scrap the project that you're working on. Your attention is going to turn to that, and you're not going to be able to keep writing your code. This is because we're helpless to the processing power of our brains. Our brains are trying to help us. They're trying to do things automatically in an attempt to help make us efficient. And these effects can be seen in what's called the Stroop task. So if you had an email account anytime around the early 2000s when chain emails were popular, this might look familiar, but it's actually real science. It's called the Stroop task, and the idea is that you're supposed to say the color that the word is written in and not the word itself. And this is actually quite hard. This is easy. It's easy to say what colors those are. It's easy to read those words. For some reason, the task here that you're supposed to do is actually pretty challenging. And the leading theory about why this occurs is that reading is an automatic habitual process, while recognizing a color isn't. So while the reading doesn't need controlled attention, it uses enough resources to reduce the amount that you can dedicate to processing the colors. All right, so now we've reached the even more human side, which I'm going to start to talk about feelings and actually interacting with other humans, regardless of if there's code involved. So I think you have to feel pretty good about yourself and have a pretty good estimate of your skill set when you're trying to write code. And something that's getting in our way of this is that unskilled people sometimes think that they are better at tasks than they actually are. And this is called the Dunning-Kruger effect. And it was inspired by the case of a man who robbed 2 banks after covering his face with lemon juice. Since lemon juice can be used as invisible ink, he thought that his face would be invisible on the security cameras. Nope. Dunning-Kruger is an example of a larger phenomenon called illusory superiority, which means that we often overestimate our abilities and qualities and underestimate our negative traits. So we think that we're smarter, prettier, and better than our friends. In a survey of the faculty of the University of Nebraska in the United States, 68% of people rated themselves within the top 25% for teaching ability, and more than 90% of people rated themselves as above average. But that's just simply, that doesn't math, right? 50% of people are above average, and 50% of people are below average. That's just the way it works. It's not to say that, those people who are below average are bad at what they're doing, right? You could be below average on your Olympic team and still be one of the best people in the world at the thing that you do. So I'm sure everyone here is below average at least one thing. I'm below average in height. And I own that. So how is this getting in our way, right? Like, you're not going to make good software if you don't realize how much more you have to learn. If you think that the way you're solving the problem is the best way to solve the problem in the world, you're not going to seek out other people's ways of doing it, and you might not actually find the best way. But there's a flip side to this too, which is that skilled people often underestimate their abilities and think that tasks that are easy for them are also easy for other people. So I think there's two ramifications of this. One of them is that if you've been doing something for a while, you might forget what it was like to be a beginner. You might lose the empathy for the less experienced programmers on your team. And if you're a senior engineer, like, part of your job is to be mentoring the less experienced engineers on your team to help them grow and become better programmers so that you as a collective unit can be making better software. And if one of the less experienced programmers on your team asks you to help them and you're like, oh, you just do it this way, that's really easy, they're going to stop asking you questions, they're going to stop asking questions in general, and they're going to stop asking the questions that you just don't think to ask anymore, which are actually helping you make better code, write better code. This could also manifest in a different way. It can manifest as imposter syndrome, which is that accomplished people feel like their accomplishments are the result of luck, timing, or deception, that they don't deserve the things that they've accomplished. And some studies suggest that this is particularly common among high-achieving women. But across the board, even some of the best programmers I know suffer from imposter syndrome. So part of my job as an engineering manager is to grow my team, and often this is by hiring people so we can get all the stuff done that we said we were going to get done. And a thing that's become very popular in hiring is referral bonuses. So you get paid money to when your friend is hired that you referred. But we tend to favor people from our own in-group, so we're going to be referring people from our social circles. And often our social circles look like us. So then you end up with a very homogeneous team. And even if I were to just refer my friends, my team would just be a group of white women, which isn't very good either. Something else that's getting in our way is called the fundamental attribution error, which means that we tend to attribute situations to other people's character rather than to external factors. So the classic example of this is that you're driving down the road and someone rushes past you and they're speeding and they're not abiding any of the traffic laws. And you're like, oh, what a jerk. They're endangering everyone on the road, when maybe they're rushing their loved one to the hospital. And had you known that, you would have had more empathy for them. And then in fact, all other times, they are a perfect driver. Yeah, it's important to have empathy for where people are coming from, because then you can accept them on your team and you can maybe make better software with them. This also applies more broadly to groups, which is that we tend to believe that the attributes of a group member reflect the entire group. And this is called the group attribution error. And I think it's very well illustrated by this XKCD cartoon. So on one side, you see two men, and one is apparently bad at math, and his friend says, wow, you suck at math. On the other side, you see a man and a woman, and apparently the woman is bad at math, and her friend is saying, wow, girls suck at math. So why does this ring so true? Well, studies have shown that this group attribution error is stronger in perceptions of groups that are more different from our own, and disappears when thinking about our own groups. So we feel that decisions made by people in our own group are the result of, structural constraints, but decisions of other groups are made as the result of their attitudes. But, perhaps it's not that other, certain groups of people don't want to be programmers. Maybe there are, structural forces making it harder for them to get into programming. Something else that's getting in our way is that we often rely on examples that come to mind when evaluating something, which is called the availability heuristic. And the classic example of this is why we're so afraid of plane crashes. So, we only hear about plane crashes on the news. We don't celebrate every time a plane successfully makes it across the Atlantic Ocean and lands. Right? We hear about the disasters and not the successes. So therefore, we think that plane crashes are much more common than they actually are. So also, if all the prominent members of our community look one way, if all the people on stage, if all the people who we see working on popular projects in open source all look a certain way, we're going to think that those are the only people who are allowed to do those things. That those are the only people who do those things. And that just, simply isn't true. We also assume that group members will resemble the prototype for that group and vice versa. And this is called the representativeness heuristic, which is essentially that categories are relatively homogeneous. So if someone is a software engineer, we expect them to have the traits that we associate with software engineers and vice versa. And this heuristic leads to several biases, such as something called base rate neglect. So Tversky and Kahneman ran an experiment in which they told participants that there was a group of 100 people, and there were 70 of them were lawyers and 30 of them were engineers. And then the scientists gave descriptions of certain people in this group to the participants and asked if they were more likely to be a lawyer or an engineer. So remember, there were 70 lawyers in this group and 30 engineers. But even when the description sounded like someone who was an engineer, people said that they were more likely to be an engineer, even though they were only 30% likely to be an engineer based on the math. So I've seen this come true at programming meetups and conferences. It's happened to me and my friends, where people come up to us. Remember, this is a programming meetup that's likely filled with programmers. They come up to us and are like, hey, are you a designer? Are you a recruiter? Are you here with your significant other? And I'm like, no, this is a programming meetup. I'm a programmer. And that's not to say designers and recruiters aren't essential to our industry. I totally couldn't do those jobs. But I am a programmer, and I want to be seen as a programmer because that's what I do, and I want to be allowed to be a programmer. So by now, you might realize that I'm talking about diversity. So why is diversity important? Well, I have some thoughts about it from a cognitive science angle. So you might remember that creativity is all about associative memory. But the more diverse your team is, or the people that you're working on your open source project with, the wider array of backgrounds, experiences, educations, and interests your team is going to have. And therefore, you're going to have a larger collective associative memory, and therefore, you're going to be more creative. So what can we do to get past this, right? First, don't feel bad. Your brains were literally programmed to do these things. Because, back in the day, our job was to stay alive. We were supposed to run away from tigers and not get eaten and find food for our families. So our brains are programmed for efficiency, to be able to think really fast so we can make those snap decisions to ensure our survival. But this is 2017. We don't really need to think fast all the time, because now, we have time. We're not in immediate danger all the time. We have, copious sources of food. We also have this, in addition to this thinking fast system, which causes all of these cognitive biases and heuristics, we also have a thinking slow system, which is more deliberate thought. And this is literally, our job is literally to think. We sit in chairs all day and we play with computers. And we think about optimal solutions to problems. So maybe if we just, sat and thought about these things that are getting in our way, thought about the more important decisions that we're making, such as, hiring, et cetera, we might be able to get past this. We might be able to assemble teams that are more diverse and that help us create better software. All right. So thanks for listening. Again, slides are there. Feel free to tweet at me or find me during the hallway track. All right.